My name is Christian Punkt. For those of you who don't know you, I'm the general manager of our Cluster of Excellence, and I have the pleasure to moderate the Science Slam. Contrary to the program, we have actually 4 contestants who are already lined up here and who are going to present their research in a hopefully entertaining way to you guys. Just a little bit about how we organize this. So we'll rate by applause today. So that means after each of the Science Slam contributions, you will get the chance to applaud. And that applause should sort of reflect how funny and entertaining you thought that contribution was. And so that this works really well, we are going to rehearse this now. So may I please ask you to give me an applause for, let's say, an okay Science Slam contribution. Yeah, that sounded really okay. How about a really good Science Slam contribution? Awesome. And now, what do you do when you're really blasted away? All right, so we have an applausometer. The applausometer is this. And if I'm unsure, I have to have you repeat this until I'm really sure who you think is the best. Anyway, so we'll get started. The first contestant is Simon Daubner. Simon studied the simulation of and numerics of solid mechanics during his master's and has now moved to battery simulations for his PhD. He's working with phase field methods in the group of Britta Nestler at KIT and really enjoys how interdisciplinary battery research is, even though communicating with chemists is like learning a new language sometimes. Okay, although he's not particularly good at dancing, he says he appreciates people who actually know how to dance, and he's going to talk about dancing with ions, whatever that means, about confusion with diffusion. Simon, the stage is yours, and your time starts now. And you get a microphone, of course. Yeah, good idea.
Thank you. So yeah, the title is Dancing with Ions, and you might wonder why I consulted ChatGPT, and it suggested that the title may capture the attention of the audience by adding a touch of elegance and intrigue to the topic of diffusion battery materials. So I hope that works out. So let's see, we're going to be talking about diffusion battery materials. There are 2 very different ways to look at diffusion. The one regime I would call optimal diffusion. We look at single ions moving in an energetic landscape. They are hopping around, and it's optimal in the sense that we have a perfect crystal structure. If they go through a transition state, we can maybe calculate the energy in between with a notch elastic band and get an idea of how diffusion works. On the other hand, we have the apparent diffusion. So if you drop some ink in water, you would see that it would spread out. And we typically would describe that by partial differential equations. We can reverse that picture and say, okay, we do have some intercalation reaction happening outside. We have diffusion into the bulk. And then here we go. This is an intercalation material. And it's still the same PDE that we're using here. There's a lot of confusion in between, so that's why I call this the realm of apparent confusion for now. And it starts with the fact that often we have spherical particles, but they are not like a solid marble on the right-hand side. They're polycrystals with thousands of small single crystals. They all have different orientations, which matters because they are anisotropic in most intercalation materials. And if we have polycrystals, then we also have grain boundaries. What do? We don't really know. So we want to solve this riddle of the in-between world. What can we do here? We can try to bridge the scales. So if we go to, for example, KMC, we can move up a little bit from DFT calculations, go to larger systems, larger time scales. Large still means couple nanometers, so it's not that large actually. Going down from this solid thing here, we can investigate the heterogeneity of these particles. So my work comes in here that we actually model polycrystalline systems. For example, we can compare randomly oriented grains with radially aligned grains and see what happens if we apply diffusion, for example, a PITT test. And what we do see is that there's a lot of heterogeneity in that left picture, whereas Allion grains definitely lead to better transport in systems. So actually, the microstructure matters, and it matters a lot. Another thing that we can do is go down to the very small scale and stretch as far as we can with continuum methods, and we go down to a single crystal. Now, this is not actually a single crystal, it's a bit simplified, but still the idea applies that we want to couple all the effects that play a role in that small scale. And if we go here, we have charge orderings, we have phase transformations, we have lattice, a mismatch in lattices. So what we can do is we simulate this, and Manu has showed it before, so we have like shrinking core principles. When there's a first order transformation, because of elasticity, the direction changes. So then we get more of like layer structure that forms, and we can intercalate and deintercalate, and we do that for different charging rates. And then we can get some information of how this diffusion actually works on the very small scale. And hopefully we can scale it up and bridge this gap between the two worlds. Thanks.
Applause. All right, thank you very much, Simon. Next up is Michelle. Michelle is a chemist by training. She studied in Karlsruhe, and she's doing her PhD in the group of Ulrike Krever. And I'm afraid it's yet another modeling talk, as if we didn't hear enough modeling work today. But here it goes. I'm sorry about that, but title of a presentation, Aging Behavior of the SCI and Sodium-Ion Batteries. I hope it's not going to get too boring. The time starts now.
Yeah, my modeling colleagues will know that reaction. So an experimentalist is standing in front of your poster and is nodding very, very politely and then running away as soon as you ask if they have questions. So I'm hoping that I can make it a bit entertaining today. My work is characterization of hard carbon anodes in P2D modeling. P2D modeling I will explain later. And basically I'm simulating the motion through the cell and electrochemical reactions, and they all run through differential equations. So, hey, it's really fun because basically it's like a poodle race. It's really nice. It's not animal cruelty because poodles just want to run to their owner, and some kind of miss because they're poodles and they're a bit dumb. But you can imagine it the same way, the transport through the battery. So that's what's my modeling system. I currently work on half cells, and in P2D means that my model is discretized. So basically, it's like the puppies are sodium ions, and some know exactly where to, and we apply a potential, so they will actually move. And some go exactly where they're supposed to go, and some kind of don't know what they're doing, so they do side reactions and form the SEI. And some are so overeager that they just sprint to the current collector and cause overpotentials because of concentration gradients. And some are just kind of lazy and just stay in the electrode and become that sodium mass. So the special thing about my model is that it has an SEI, and you can simulate transport through it. So we have those nice equations, and that's where it really gets fun, right? The math. Math? No? Okay. But basically, those are my reaction rates, and if I put all of them together, I can simulate the voltage curve of the battery cell. Yeah? So basically, I have rate equations and transport equations through the SEI, and I have a lot more. Hey! Okay. Is this exciting enough for you? Huh? Yeah. Because like these bubbles, we can imagine the SEI like those bubbles, because actually it has two surfaces, one inside, one outside. And those surfaces are kind of like doors. And when you have those puppies and they have to run through doors, like if you have a low current, they kind of run through like they want. Yeah, that works. But if you have a lot of puppies, there's a certain rate limitation, and it just takes some time for the puppies to finally get into the water. So with my motion equations, I can basically explain rate limiting in our battery systems. So thank you for taking your time with the simulative work. Thank you for my roasters. That was obviously planned. They're nice people. And thank you for listening.
Thank you. Well, that wasn't too bad. I'm happy. So next up is Soutam Panja. He's a PhD student in Max Fichtner's group and works on chloride-ion batteries. He has a background in chemistry, completed his bachelor and master degrees in this field, and he also has some experience in battery research, having worked for a few months on different types of batteries. So he says he's very passionate about his current project, which aims to develop novel and sustainable chloride-ion batteries for various applications. What made me a bit concerned was that he stated that he likes to watch movies, for example, like zombie apocalypses and such like that. I hope you don't see a chloride-ion battery apocalypse now. So the title of your talk, Chloride-Ion Batteries, Unlocking the Potential for Sustainable Energy Storage, and your time starts now.
Hello everyone, myself Soutam. Today I'm going to discuss about the chloride-ion batteries, unlocking the potential for sustainable energy storage. As Christian mentioned, that I really like the zombie movies so much that I sometimes get dreams that I become a zombie. So I'll try to explain in such a way that I became a zombie. So I'll just mention this as me, as a zombie. Yeah, I could call it as a Mr. Soutambi. So I want to expand my army. So there are some few research assistants there. I also jabbed them with this called brain jabbing device. And so they are in my army now. So, but somehow I found that this machine is not working because this battery is out of charge. So I want to charge it, but I don't have any such material. So I look around and found here a bottle of bleach, a bag, a fertilizer, and an iron wire. So I just started thinking that how I can make the battery out of it and make it charge my device out of it. So then I just mixed the bleach with the water, and there was the fertilizer. I mixed also with water. So then I connected my device with these two kinds of system, one fertilizer solution, one is the sodium hypochlorite solution, and then I connected my device with it. The iron wire reacts with sodium hypochlorite solution and forms iron chloride. There is one chloride ion, there is one electron that passed to to the fertilizer system, and then there is a continuous flow of electron, and I somehow found that, oh, the device is getting charged. So I am very happy that I can make the battery out of a chloride ion shuttling system. So now I can do the zombie apocalypse now. So is there any other thing that I can do from, the zombie apocalypse? No. There are several advantages in real life as well. That's not a dream. There are several advantages of abundant material resources. It's cheap, it's highly processable, it's high theoretical energy density. Talking about this charge-discharge mechanism, where this iron chloride cathode, the chloride ion shuttles, and it reacts with other metal anodes, and it forms another, through the conversion reaction, it forms metal chlorides, and it's come back through the chloride ions. So, but there are some challenges that there's metal chlorides with the organic solvent. There are side reactions that's happening. But there are some other examples of a better cathode as well. There are some metal oxychlorides that are highly stable with the organic electrolyte. When I joined 5 months back, I wanted to check how the chloride ion system worked. So I quickly synthesized it, did some characterization, did some experimental studies, and found that it's working. So what I'm currently doing, I'm doing on iron chloride cathode for chloride ion batteries. Yes, it's possible. We can work on cathode as iron chloride, but it's like highly challenging. We should consider several factors. And let's talk about my future perspective. I want to work on how this dissolution work and how this chloride ions dynamics is happening. And in future, I want to prepare a novel electrolyte solution so that I can suppress the dissolution of chloride electrodes, metal chloride electrodes. So thank you for your attention. As mentioned, there are not just a bunch of salty jokes. There are promising technology for our future energy storage. Thank you.
All right. Well, I'm glad you didn't really turn into a zombie, but are still yourself. Excellent. So last, but certainly not least, Mahla Talari. She studied chemistry at KIT. She's working on her PhD in Helmut Ehrenberg's group on electrolytes for aluminum batteries. I should say aluminium batteries. I'm not lazy. So everybody had to give a sort of a little funny statement for me for moderation. Mahla told me she exhausted her funniness reservoir so much in preparation her slides that she didn't have anything for me. So I'm guessing it's going to be great now. So Mahla, the floor is yours. Title of your presentation, In Pursuit of Heroes, Unveiling the Secret of the Non-Corrosive Electrolyte in Aluminum Batteries. The floor is yours, and your time starts now.
Okay, why cats are so good in playing poker? Do you have any ideas? So maybe we found out. So lithium is the king of the battery worlds, but now, like a leopard, he is endangered, and therefore he agreed to share his kingdom with other rulers as well. And one of the candidates is actually aluminium. You can easily find it, and also, in theory, he can be a king. Actually, I believed he already thinks himself as a king. But then, using the aluminium as a negative electrode, it's not like a honeymoon. There are problems, and the most important one is the passivation layer of the aluminium. It's like a fur coat. It gives the prestige to the cat and also empowers him. But at the same time, it hinders electrochemical reaction to take the place. And it's like the people here who have a pet know how hard it is to get rid of the cat hair from the sofa. It's the same situation here. So we actually need an electrolyte which actually destroy this passivation layer and enable the aluminium to be plated and stripped on the surfaces. Fortunately, we have one option. It is a really high corrosive electrolytes, and it's really talented to destroy the passivation layer. At the same time, these troublemakers can get really wild and destroy everything else in the system as well. So apart from the safety concern, they also left us with a really limited choice of column collectors. So after countless hours of research and endless cup of coffee, finally these curves have broken, and they come up with a new electrolyte. They said, okay, this electrolyte makes the aluminium magically plated and stripped on the surface of the platinum electrode. And guess who got really interested in this electrolyte? Our group. I was so interested that I could fit myself in 2 chairs. But then we got to do a little bit serious stuff as well. So we did one cyclic voltammetry, and we could also observe the reversible current, which was believed to be aluminium. After that, of course, it wasn't enough for us, so we took our magnifier to look a little bit closely to the surface to really find them. And unfortunately, despite the fact that we really wanted the aluminium there, we couldn't detect any. So we have to arm ourselves with more fancy stuff, and we were watching the reaction while they were taking the place with optical microscopy images. And shockingly, there was a reversible gas was forming on the surface of the electrolyte. Of course, we were suspicious, and we did analyze this gas. At the end, we realized shocking news. It was hydrogen evolution reaction, which was responsible for the current that we observed in the surface. So although we really wanted him, we found her. And we don't have any king, but we have a queen. So I'm going back to the first question. Why are cats so good in poker? Of course, because they have the poker face. You cannot know what they are thinking, what they are doing, and they can easily mislead us. And this is the same with aluminium. It's so challenging that you can easily get wrong information, and it's a little bit hard to understand. But the good thing is that we have no fear, and we have our lab coats on. So thank you for your attention. And I would like to say the pictures were generated by AIs. They are not as intelligent as you think of.
cat pictures, of course. So I think I think the ladies did a pretty good job. So from what I heard, but I think I want to ask you, all four of you on the stage already, and I think we want, come on up. But I think I'd like to hear 2 more rounds of applause, one for Michelle and one for Mahla, so that we are really sure who you think is the best contender. Sorry guys, but I think it was pretty clear, right? Yeah. So first round of applause, Michelle. You are aware this was the okay applause, yeah? Okay, so how about Mahla? All right, she didn't just bring cat pictures, she also brought her fan club. Excellent. Congratulations, Mahla, you are the winner of today's Science Jam.